In the last few times, we've been going over the thermodynamics of chemical reactions. Especially, we've been focusing on the driving forces that cause chemical reactions to either go forward or backwards, and which are all balanced at equilibrium. And we derived this general formula that gives the driving force in terms of the change in the Gibbs free energy per mole. And we saw that that's equivalent to looking at the difference in the chemical potentials, the net chemical potentials for the products and the reactants. And so it's literally a driving force. It's the degree of imbalance in chemical potential between the products and reactants. We saw that if we set this equal to 0, which means we are at equilibrium, then we can derive this relationship, which says that the equilibrium constant is equal to the reaction quotient Q when all the reactant and product activities are at their equilibrium values. And we've seen in the last couple of times in the examples we've gone through that how that works and what that allows us to do. We also saw earlier that the equilibrium constant is closely related to the standard state Gibbs free energy change for the reaction. That is, the Gibbs free energy change when all the reactants and all the products are in their standard state concentrations and pressures, and at the table temperatures, depending on where you got the delta G0 value. And of course, we can invert this relationship and find the standard state Gibbs free energy change by measuring equilibrium constants. And in fact, that's done. Some of the table entries that we use in order to do these calculations from tables, from thermodynamic tables, originally came from measuring product and reactant concentrations at equilibrium, using this relationship to get the K value, and then taking minus RT log of that in order to get a delta G value. All right. Now we're going to go on and look at a few more things that are related and relevant to this same topic. And one of those is just to get a little bit better understanding of where the entries in the tables come from, and the thermodynamic tables come from, and why those particular entries are in the thermodynamic tables to begin with. And that one of the reasons is this idea or this concept or this rule that is called Hess's law. What Hess's law says is that if I have a particular chemical reaction, I can change the path by which that chemical reaction takes place, and it doesn't change any of the thermodynamic values, and not any of the state function values like delta H, delta U, delta S, and so on. Of course, that's true, but let's see how it works out in the context of thermodynamic tables. So first of all, we're looking at the entries in the tables, which are state functions, delta H, delta U, delta G, and delta S. Any one thermodynamic table usually doesn't have all 4 of these, but they'll have usually oftentimes 3. Delta U, delta H, delta G, and delta S are the 3 most common. And from those, you can calculate the delta U value, so it's equivalent to knowing delta U as well. All right, so let's consider then an entry in the table. Usually what's listed is just a compound, a molecule type in a particular phase state. So a common case is liquid water. And it's listed that way in the table, but what that really stands for is a chemical reaction, not just a compound, not just a single species, but an entire chemical reaction. It stands for the formation, the chemical reaction that causes the formation of the species in question, water in this case, from the elements, hydrogen and oxygen, in their most stable states. In other words, no matter which compound we're talking about, start with all the elements that you need in their most stable state. So oxygen, for example, would be in the gas phase at room temperature 298, and hydrogen gas would also be in the gas phase. If we were talking about CO2, let's say, the elements would be C, carbon in the graphite phase. Graphite is the most stable form of carbon at room temperature and pressure, plus some oxygen. Let's see, yes, just one oxygen molecule going to CO2 in the gas phase, and oxygen also in the gas phase. And so here's the most stable state of carbon, here's the most stable state of oxygen, and that produces CO2 at the table conditions. And that's what this entry for CO2 in the table stands for. It really stands for this formation from the elements reaction. Then Hess's law gets applied. So what we have are delta H's, delta G's, delta U's and stuff for the formation of, let's say, so let's consider this chemical reaction, for example, the burning or combustion of methane. So we start with the methane, we combust it with oxygen, we get CO2 and we get water. It's important, of course, to specify what phase state each of the reactants and products is in. So gases for methane, oxygen, carbon dioxide, and liquid for water. We say, well, that's equivalent. Taking this reaction straight across is equivalent to going around by this other path. That's Hess's law. And we choose the other path to be the following. First, we take apart all these molecules into their elemental forms. So we take the methane apart into carbon and hydrogen. We take the oxygen. Well, the oxygen doesn't have to be taken apart. It's already an element. And then we reform those same elements now into new molecules like carbon dioxide and water here. And so the overall net, let's say, delta G value, but it would be the same for delta H or delta S, would be that we lose a certain amount of delta G on this side, right? This arrow represents the reverse of the formation reaction, so we get minus signs. And then on this side of the path, we get plus signs because we're actually forming here we're destroying the molecules and turning them into their elements. Here we're forming the molecules from the elements. And the net result is that if we take the whole result, then the delta G overall is equal to, let me see, I didn't write it down here, let me write it down. Delta G for reaction would then be equal to this guy, delta G CO2 plus 2 delta G H2O, and this is gas, this is liquid, minus this guy, which is delta G CH4 gas plus 2 delta G O2 gas, right? Which is exactly the rule that we've been using all along, right? It's products minus reactants weighted by stoichiometric coefficients like these 2's that appear because there's 2's here and here. All right, so Hess's law explains why the tables work in the first place. They basically amount to substituting the straight reaction for this slightly more circuitous reaction that takes us through the elements instead of just straight across. Now, that works really well for all of, this rule works for all of the types of state functions that appear in the tables, but we should say something more about one of the entries, namely the entropy change itself, because those entries are a little different, right? For delta H, delta S, delta U, it's delta H, delta G, delta U. In other words, a change in H, a change in G, a change in U for the formation, for a reaction that amounts to the formation of a particular compound from its elements in the most stable state. But for S, it's not that. For the entropy, it's an absolute entropy. There's no delta in front of it. It's an absolute entropy that represents the change in entropy starting from, let's say, pure water in the solid form at T equals 0, at absolute 0 of temperature, and then taking that same substance all the way up to whatever the final table temperature is, 298 K usually. That's an absolute entropy because the third law says that the entropy is equal to 0 when the absolute temperature is equal to 0. So if we start out at absolute temperature of 0, then we know that the entropy there is 0, and therefore the entropy change, if you like, is an absolute entropy. It's not a delta S, it's an S And notice, too, apart from the fact that this is a third law absolute entropy, the other thing to notice is that this isn't the entropy of a chemical reaction. It's the entropy for a warming process. We're not doing any chemical reactions. We're not taking the bonds apart and re-putting them together in some other form. We're not breaking the water down to elements or anything like that. We're just warming the water up. Starting from ice at 0 degrees C in a perfect crystal where the entropy is 0, we just warm things up, and then let me go down here a little bit. In the course of warming things up, we do all the calculations that we need to do in order to calculate the delta S change, right? So if we're warming up ice, frozen ice, we use our standard formula for calculating the entropy change due to a warming up process at constant pressure of 1 atmosphere here. Then we go through the phase change, the melting process, because it's liquid water that we want in the end. And that's just the delta H of fusion at the temperature, let me make that the temperature of the melting point. And then we add the entropy due to the warming process from the melting point on up to the final temperature, which is usually 298, not necessarily. And again, all this at constant temperature. So the entries that for the entropy in the tables aren't the same kinds of things that the entropies for delta H, delta S, and delta G are. Delta H, delta U, and delta G are. They're different kinds of things, both because they're absolute entropies and also because they represent basically just a warming and maybe melting or maybe even vaporization process, but nothing more than that, no chemical reactions. Now, why this particular change rather than a chemical reaction? Why aren't we looking at the entropy change for the formation of water from a chemical reaction like we are in the other cases? Well, the reason is that if we look at the entropy change for a chemical reaction, the thing you measure is the heat that's released or absorbed by the chemical reaction when it takes place. But that heat isn't the entropy change of the molecules themselves. That's the entropy change for the surroundings. In other words, the quantity that you would measure for the entropy change of a chemical reaction in the normal process of doing things isn't the right entropy. We want the entropy change of the molecules themselves, not the entropy change in the surroundings caused by the release of heat to the surroundings or absorbing heat from the surroundings. What we want instead is something like this. Here's our same chemical reaction again. Methane and oxygen goes to CO2 and water. If we are at 0 degrees temperature, then there's no translational motion, right? No rotational motion, no vibrational motion. Same for all these other molecules. If you're at 0 temperature, all those motions are frozen out. And that's why you have 0 entropy change. Let's see, I have a little thing that shows that a little better later down, I guess. That's why you have 0 entropy when you're at near 0. All the motions have been frozen out. There's only one quantum microstate available to each molecule and one quantum microstate available to the whole ensemble of Avogadro's number of molecules, and therefore the entropy is 0. As you warm up, though, towards 298 K, and go through phase transitions if there are any, then all these degrees of freedom turn on. There start to be a lot of translational microstates, possibly. There start to be a lot of rotational microstates. There start to be vibrational microstates and so on. So the system, each of these molecules gains a certain amount of microstates. And like I say, we want to measure that, and the way we do it is by measuring heat capacities. So you need heat capacities here, and over the course of a temperature change, and then doing these integrals in order to calculate the entropy as the temperature change takes place. So it's a fundamentally different kind of thing for entropy than it is for the other things. All right, so yes, what we want is the number of microstates for each degree of freedom. We want to see the changes in those things that occur in the course of a chemical reaction. So let's look at our chemical reaction again. And this time, let's think not about free energy, but about entropy. We first take our reactants here, we freeze them down to 0 degrees K, where the number of microstates available to them is just 1 for each case, therefore no entropy on this side. Now we take those molecules apart, put them together. That doesn't involve any change in entropy because nothing's moving. There's only 1 microstate for each of the molecules on this side too. 1 microstate on that side, 1 microstate for each thing on that side. No change in entropy. So the chemical reaction doesn't have any entropy change down here. Now that isn't quite true, and there are some subtleties and difficulties with what I'm just saying, but that's the gist of it. That's the idea. Then we warm things back up on the other side, and this is another application of Hess's law, right? This going by this route is the same as going by that route. And so the absolute entropies that we are, and this actually measures, of course, the kinds of changes in the degrees of freedom of the molecules themselves that we need in order to do the calculation. It's not the entropy of the surroundings anymore. This truly is the entropy change in the molecules themselves. All right. And I think that is all and so if you then, go through this cycle, you can see that again you get the same rule for using the tables to get a delta S of reaction that you get for everything else, right? In the end, there isn't any practical difference in how you use the tables between entropy and everything else, but it's good to know that the entries in the table are somewhat different, a different kind of quantity than the entropies for delta H, delta S, delta H, delta U, and delta G. All right. There are some rules for combining delta H's, delta S's, delta G's, and delta U's, and equilibrium constant values when you have multiple reactions. So here are the rules. Rule number 1 is, let's suppose I have 2 chemical reactions. A plus B goes to C, and then C goes to D. The overall, if I add these 2 reactions together, the overall chemical reaction is A plus B goes to D, right? Because the C's here cancel. And let's suppose that from the tables or from some experimental measurement perhaps, we have a delta H for this first reaction. We also have a delta H for this second reaction. Let's suppose also we have an equilibrium constant for the first reaction and an equilibrium constant for the second reaction. Then what's the delta H for the overall reaction? After we've added these 2 reactions together, well, it turns out that rule number 1 is that the delta H for the sum of 2 reactions is the sum of the delta H's for those reactions. That sort of seems intuitively reasonable. For the equilibrium constants, though, the rule is that the overall equilibrium constant for the overall reaction is the product. You multiply the 2 equilibrium constants together. You don't add them. Adding them will give you a totally wrong result. Always multiply equilibrium constants. So that's rule number 1. Rule number 2 is that if I take a chemical reaction and I multiply it by something, in this case I've multiplied by 2, but I can multiply by anything else, pi or square root of 3 or anything else. So this new reaction down here is just a multiple of the top reaction. Let's suppose I know the delta H for the top reaction, then the delta H for the multiplied reaction is just multiplied by the same constant. That makes sense, right? You've basically got twice as many moles taking place or changing in this lower reaction than you do in this upper reaction, and so it makes sense that the delta H should be multiplied by 2. On the other hand, for equilibrium constants, instead of multiplying the equilibrium constant by 2, you square the equilibrium constant. Instead of a multiplier, you get a power for the equilibrium constant. So if we multiplied by, let's say, pi here, pi A plus pi B goes to pi C. So pi, of course, is not an integer, not even a rational number, not even an irrational number. It's a transcendental number. It doesn't matter how complicated the number is. Then you would get that the equilibrium constant for this new reaction is k to the pi power. It doesn't matter what the power is. Whatever you multiply by, that's the power that you raise k to in order to get the new equilibrium constant. That's rule number 2. Rule number 3 is that if I reverse the reaction, if I turn the reaction around, then I reverse the delta H and I invert the value of the equilibrium constant. So A plus B goes to C. The reverse of that is C goes to A plus B. If I know delta H for the forward reaction, then it's minus delta H for the backward reaction. We've actually been using that rule all along since it's kind of intuitive. I don't think anyone even noticed that we used that rule without saying what the rule was, but we did. For an equilibrium constant, though, it's not quite so intuitive. The new equilibrium constant for the reversed reaction is 1 over K rather than anything else. So you invert or take the reciprocal of the original equilibrium constant if you reverse the reaction. These rules for K might seem a little strange at first. Everything's getting multiplied or raised to powers or inverted instead of these more intuitive rules for delta H. And let me say, I'm using delta H here, but the same rules apply for delta G or for delta S or for delta U. All of them, all the sort of standard thermodynamic quantities obey the same rules. It's just the equilibrium constants that have these somewhat funnier rules. But the rules for equilibrium constants follow from this relationship. The equilibrium constant, remember, is essentially an exponential of one of our more standard quantities, delta G. And that's why, because exponentials have their own rules, right? They basically turn pluses into multiplies. They turn minuses into divides. Because of that, the equilibrium constant obeys these different rules. Let's see how that works. Let's suppose, for example, that I'm adding two chemical reactions. So this is rule number 1. A plus B goes to C. C plus C goes to D. Therefore, A plus B goes to D. Using the rules, the standard state delta G's become the sum of the two standard state delta G's. So let's see what that does to the equilibrium constant, right? The equilibrium constant for this overall reaction should then be E to the delta G for the overall reaction, which is delta G1 plus delta G2. Now using the properties of exponentials, that just factors, and you end up getting the rule for equilibrium constants when you add two reactions, namely multiplying the two equilibrium constants. It follows directly from the definition de facto of the equilibrium constant. And that has to be true, right? We couldn't have this relationship be true and also this relationship be true unless they were consistent with each other. So if you wanted to, I guess, you could derive all these equilibrium constant rules by looking at what the equilibrium constant would do given its definition in terms of delta G, by calculating delta G and then using that to calculate the equilibrium constants. I don't recommend that. It's a little bit of a roundabout and unintuitive way to get an equilibrium constant. It's better just to use the rules, but you could do it. All right. Now we come to sort of the main topic, I think, for this lecture. I don't think we'll finish with this topic in this lecture, but we'll get it started at least. And that's to start talking about how the equilibrium constant itself changes with temperature. Earlier we saw Kirchhoff's rules, right, to see how delta H and delta S change with temperature. Remember, delta H is equal to delta H at the table temperature, let's say 298. Usually these are standard state delta H's, plus delta Cp times delta T, and delta S is equal to delta S at 298 plus delta Cp log T2 over T1. Those are Kirchhoff's rules, and they give us a way to calculate changes in delta H and delta S when the temperature isn't the same as the table temperature. But what about the delta G value and the K value? Well, for the delta G value, it's pretty easy. We can use this relationship, right? So if we want delta G at a different temperature than the table value, we can calculate the delta H at that temperature, the delta S at that temperature, and then plug those values into this relationship using the correct final temperature there, and we can get the delta G. So that's for a constant, yeah, okay. And so that's not too hard, but what about the equilibrium constant? Well, it turns out, I mean, we could do the equilibrium constant in the same way by plugging a delta G value in here now. That could be done. But there's a somewhat more convenient way of doing the same thing. And that's to use this Van't Hoff equation, or Van't Hoff relationship that we'll now talk about. I'm going to do a sort of simple, not entirely rigorous derivation of the Van't Hoff equation. Here it is. K at temperature T2, our final temperature, divided by K at temperature T1, our initial temperature, using the definition of the equilibrium constant, is equal to e to the minus delta G at the final temperature, divided by e to the minus delta G at the initial temperature. Now remember, these delta G's are also, this one has to be at T2, and this one has to be at T1, so these two delta G's aren't the same. And now I can substitute in, for these delta G's, the delta H minus T delta S definition, and when I do that, this T2 divides out, this T1 divides out, I get e to the minus delta H over RT2 times e to the delta S over R. I get e to the delta H over RT1 times e to the delta S over R. And now these two delta S's really are the same thing, so they divide out. And that results in the Van't Hoff equation. So it's a pretty short derivation. This one is, it's not the best derivation, truly. I apologize a little bit to those who've seen better derivations elsewhere. I don't want to go through the full derivation because I don't think it's that valuable. It doesn't give much insight, and it would take some time. So this is not the best derivation, but it's at least one that gives you the right answer and seems kind of intuitive. And here it is, the Van't Hoff result. It says that the ratio of the two equilibrium constants, one at the initial temperature, one at the final temperature, is equal to e to the minus the delta H for the chemical reaction in question, divided by R, times the difference in the 1 over T's, right? 1 over T2 minus 1 over T1. I can take the natural logarithm on both sides of this equation, and then I get this result, natural log of K2 over K1 is equal to, now it just gets rid of this exponential, right? Minus delta H standard state over R times 1 over T2 minus 1 over T1. And I can basically call this T instead of T2 and just treat this like a constant, and if I do, then I get this relationship, which is really the most general form of the Van't Hoff relationship, which says that the logarithm of the equilibrium constant is equal to, and these are all approximately equal to, by the way. There are approximations in this. Basically, let me say something about that. I'm assuming in doing this derivation, and even in the more rigorous derivations, the same assumption has to be made, that this delta H and this delta S also don't change with temperature. The only thing that changes with temperature is this T2 or this T1. So we're assuming that these guys are constant with temperature. That's only true over a reasonably narrow temperature range. If the temperature range gets too wide, then these relationships are no longer correct, and you have to use some more complicated relationships. That is probably not something, well, for certain is not something we're going to do in this class, but I warn you that there are cases, if you've got a 100-degree temperature range or a 200-degree temperature range or something like that, then probably the delta H's and delta S values haven't stayed constant over that full temperature change. And then you've got a more complicated result that you've got to work with. And we can talk about that if people are interested, but it comes up rarely enough that you don't normally encounter it. So these relationships are only good for about a 50-degree temperature range. Any temperature range, any change in temperature between T1 and T2 that's bigger than about 50 degrees, well, the practical thing to do is do the calculation this way anyway, because it's the easiest thing to do. But you got to be a little worried that maybe Van't Hoff is seriously off by the time you've got a bigger than 50-degree temperature range. So that's a warning. All right. So we will use these relationships in some examples in a minute here. But let me point out, and the last example will be what's called a Van't Hoff plot that we'll do in a minute here, or in a while here. The Van't Hoff plot is the plot that you get from this particular relationship. Notice that if I call this quantity y, I consider it to be the thing that I'm plotting on my y-axis here. And I call this quantity x, that's the quantity I'm plotting on the x-axis here. then this is the equation for a straight line, right? Y equals slope m times x plus a constant, which we call b. And that means that if I make a bunch of measurements of equilibrium constants at different temperatures, and I then plot the logarithm of those measured equilibrium constants versus 1 over the temperature, and then I take the slope of my plot. First of all, I should get a straight line, and it's kind of a test for whether this whole theory is good or not, whether you get a straight line. If you don't get a straight line, and your data are good enough to see that you're not getting a straight line, then you know that the whole Van 't Hoff analysis is not good. You've got to do something more complicated. But presuming you get a straight line, and I've never encountered a situation where you don't get a straight line, you know, pretty much always do get a straight line, then the slope of that straight line is the same thing as minus delta h divided by r. And so it allows you to get, that slope allows you to get the sort of best possible, I mean, there might be all kinds of noise in these data, right? So taking a least squares line through the data and presuming that it really is a line and not something more complicated, then this allows you to get a good value, a good, well-justified value for the delta H for the reaction. So you take the slope and multiply by minus R and you get the delta H. We'll do that down below. All right, let's look a little bit at what the Van 't Hoff relationship is saying, and then I think we'll probably stop after that to do the examples for next time. So first of all, here's our Van 't Hoff relationship. It involves, so the ratio of the equilibrium constants here is controlled by the delta H value and no other thermodynamic value. It doesn't depend on the delta S, it doesn't depend on the delta G, just depends on the delta H for the chemical reaction, the standard state delta H for the chemical reaction in question, and then of course it also depends on the temperature change. So let's suppose, for the sake of getting things straight, that we've raised the temperature in the course of some changes. So we've gone up in temperature, and that means T2 is bigger than T1. That means 1 over T2 will be smaller than 1 over T1, which means this whole quantity will be negative. So 1 over T2 minus that quantity, 1 over T2 minus 1 over T1 will be less than 0. If I think about what that means up in this exponential, that means this whole quantity will be positive, right? So that minus sign right there means this whole quantity is positive. And that means that whether this exponential, whether this quantity up in the exponential is positive or negative depends on whether delta H is positive or negative. So if delta H is positive, that means this whole quantity will be positive. And that means that this exponential will be bigger than 1, and that means that K2 got bigger than K1, right? K2 over K1 is then greater than 1, which means K2 got bigger. So the rule is that if I have a positive delta H, which means that my reaction was endothermic, then when I change the temperature, the equilibrium constant will get bigger. And it works the other way, too. It means that if I change the temperature and I observe by measurement that the equilibrium constant increased, then I know that I have an endothermic chemical reaction. I have a chemical reaction that absorbs heat in the course of the chemical reaction. On the other hand, if my delta H value is negative, which means an exothermic chemical reaction, a reaction that gives off heat to the surroundings instead of absorbing heat, then according to the Van 't Hoff relationship, the equilibrium constant will actually go down. And again, in reverse, it works too. So if I observe that the chemical reaction goes down, then I know that my reaction was exothermic. Whether I can tell that by other means or not, right? It's oftentimes easy to tell that a chemical reaction is exothermic because it warms up. You have your beaker, and you run your chemical reaction, the beaker gets hot. That's an exothermic chemical reaction, but now you know that that also means that if you then change the temperature at which that chemical reaction takes place, the equilibrium constant for the reaction actually goes down. So here's our rules. K increases with temperature if the reaction is endothermic. K decreases with temperature if the reaction is exothermic. There is a way to rationalize this result beyond just thinking about the Van Hoff relationship. The Van Hoff relationship shows that this result is true, but there's a way to sort of understand it qualitatively using Le Chatelier's principle. So I should have written Le Chatelier up here. Let me do that now. Le Chatelier's principle says that if I have a chemical reaction like this, and I add a reactant to the chemical reaction, then I push the equilibrium towards products. Adding the Le Chatelier principle says that the reaction always tries to oppose what you're doing. A reaction that's already at equilibrium, if you make a change, the reaction will change in a way that opposes whatever you're trying to do. So if I add heat, the reaction will try to absorb that heat, but that means moving the reactant towards the reaction towards equilibrium. That means raising the equilibrium constant. So raising T is like adding heat, which is like adding a reactant. That pushes the reaction towards products, and that means that the K has increased. On the other hand, if it's an exothermic reaction, everything reverses. So in that case, heat is effectively a product. Raising temperature is like adding a product. That pushes the reaction back towards the reactants, and that means that that's the equivalent to saying that the equilibrium constant for the reaction decreases. All right. A second thing to say is that which way the reaction, so the first thing to say here, number one, is that which way the equilibrium constant changes tells you about the sign of delta H. What about the size of delta H? Well, what the size of delta H controls is how sensitive the equilibrium constant is, or how sensitive the reaction, for that matter, is to changes in temperature. If the delta H for the reaction is just not very big, not much heat is lost, not much heat is gained, doesn't matter, then according to our Van Hoff equation here, this is a small quantity. Changes in temperature multiplied by a small quantity don't make very much change, and that means the equilibrium constant is insensitive to temperature. On the other hand, if the delta H is a really big delta H, now changes in temperature will make a big difference in what's up in the exponent here, and that means that the equilibrium constant is sensitive to temperature. The reaction is sensitive to temperature. The position of the equilibrium will be affected greatly by temperature. So the size of delta H, whether it's positive or negative, the size of delta H controls the sensitivity of the reaction to temperature. The sign of delta H controls which way the reaction shifts when you change the temperature. All right, with that, we'll stop and pick up the examples, begin doing some examples here. I have several examples to do next time.